Good morning, everyone. We have a few small announcements, few small updates based on the class size. So we seem to be having a slightly bigger class size compared to what we had anticipated. You might have seen that the course website has been updated. We have now mentioned all the TAs, as well as the prerequisite exam has already been released. So the deadline has been mentioned to be 6th January 9 p.m., which is tomorrow. So you have to send in the solutions to be able to take the course, right? And this is a hard deadline. The grading policy, there has been a very small change. Previously we'd mentioned groups of 5, but now we're saying 6 or 7, where 6 is preferred. That's just keeping in mind the larger class size. Apart from that, in the FAQs we have mentioned a couple of new things. One is the audit policy for people who want to audit. Second is the computational resources. Some of you might be worried that how you'll do the assignments. We will be providing you with Google Cloud Credit or something equivalent pretty soon, right? As soon as that gets approved. Any burning logistical questions about the course? Okay, good. So before we start the main content of today's lecture, I want to usually start each lecture with some new technology, something new machine learning, which is being deployed. So today I want to show something known as PoseNet. So in the camera, if you see, you can probably see it's tracking my eyes, my ears. But if I move back a little, if I just go back a little, you can see that it's actually trying to capture my entire skeleton. And then you can use it for various applications. Where might you want to use? Where do you think you could use such an application? Louder? For animations? Okay, perhaps you want to use it for animations. What else? So what event just happened in our campus a couple of weeks back? Inter-IIT. Can you use something like this for inter-IIT sports? How will you use that? Let's imagine that we notice that like as it's very common, there will always be more, let's say, athletes than coaches available. So could you do some personalized training for them? Could you figure out that certain exercises they're not doing properly? Or let's say if they're doing certain sports, if they're doing a javelin throw, can you look at the angles at which they're throwing the javelin? All of that you can do using such technologies. And this is from Google, so they have a very nice blog post on this. Interestingly, this is running on something known as TensorFlow.js. Mostly when we think about machine learning, we think about Python. Right? That's the first language which generally comes to mind because of the very good ecosystem. But this is TensorFlow.js running on JavaScript. So all of this is running within the browser itself. Doesn't need anything on the server side. So in this blog post, they nicely mention, they give some very interesting demos of people dancing. They can also look at the angles at which people are trying to pass the ball. So in this case, if some of you have played football, you might see that this is a dummy pass, something like that. You're not directly looking at the ball, but you're still passing. So someone like Ronaldinho was supposed to be very good at this. You can also see Roger Federer, and you can see the angles at which, for example, the knees are bent. Imagine if someone is recovering from a knee surgery. Now you can tell them that you need to be very careful with your knee. You can't bend it beyond a certain degree. So such things are possible if you can have scalable solutions. So in the last lecture also we said that you're trying to use machine learning, we're trying to scale things. Right? So let's say if you didn't have this solution, computer vision based, machine learning based solution, what might you have done to still be able to track such things? What could be some other alternative?
We can do some bend sensors along the.
Okay. So Jaydev says that you can perhaps put dozens of sensors, and if some of you have watched Shark Tank, you might have seen there are certain solutions being proposed where they suggest that you can put dozens of sensors on your body, which will look at your accelerometer readings, your gyroscope readings across the different parts of the body. Right? You could use that, or you could use a computer vision based technology. And if you want to take this a step further, you could also, for example, play rock, paper, scissors. This is just for fun. but it's basically an extension of the same. Right, so now it's, if I put, okay, sometimes the demo don't work, but this is not on me. I was expecting it to show something. Let's try again. Okay, this is not a rock, definitely. This should be paper. This should be scissors. I don't know, but okay, at least scissors it was. Okay, this is not rock. And thankfully for us, they've also written that if the model didn't work for you, it's basically that was created on, no, I'm not a scissors. So don't feel bad if it didn't work for you. And this worked for me when I was sitting in the office yesterday. So this will be one of the part of your first assignment, that when you go and deploy solutions, you will see how badly they fail. So you want your solutions to also fail gracefully, but that will generally not happen. Like this was a very, very rudimentary example. So in your assignment, you will actually be looking at, as I mentioned last time, you'll be looking at the accelerometer data from your smartphone. If you'll use the public data set, you'll show me 95% accuracies. When you run the same model on the data that you collect, you'll maybe get 20% accuracy, 30% accuracy. And that's when you'll realize why the engineers at the Googles, the Apples, the Samsungs are paid so highly, so that the solutions are robust across various scenarios. Okay, any questions? We will revise what is machine learning. We looked at this definition in the previous class. We look at this definition and we'll want to see how machine learning is different from, let's say, your regular data structures course. So the definition, as per Arthur Samuel, this was 1959, is the machine learning is the field which is about the study of computers, giving them the ability to learn without being explicitly programmed. Can someone tell me what you understand by this statement? Without being explicitly programmed? Does this mean that if you are a machine learning scientist or an engineer, you don't need to write a program? So then should you be a machine learning theorist? Is this what it means? Any guesses on what this might mean? Without being explicitly programmed? You don't? You don't program every case. Okay, that's pretty much online with what I had. Any other answers? So many of you who've not been exposed to machine learning, whatever programming you have been doing is generally called traditional programming, like what you did in your data structures course or your computing course. We will understand this with the help of an example. Let's take the first problem in the course. This is digit recognition. So we are given a bunch of digits and you want to recognize them from 0 through 9. Just to make the problem simpler, we have told you that we have given you the digits in a 28 cross 28 dimensional box. Where do you think you might use a technology like this for digit recognition? Okay, someone from the first row. Someone, first row, first column. Where might you use digit recognition? Counting? Counting notes. Okay, so you might be using them on currency notes. Similarly, on that line, you might be using them for automating check processing. Right? So early days, checks many times used to be handwritten, or many of you filled out your JE forms or your different forms. In the days when they were not digitized, you had to actually write them. And some of those things, if you put a human being, they may take longer and they may also make mistakes. But if you put a machine, in such cases, the technology has become very robust. Where else you might you use digit recognition like problems?
Automatic answer script evaluation.
Okay, answer script evaluation. So Jaydev is very optimistic about my handwriting. At least with my handwriting, I don't expect this to work. It might not even detect it to be English. So, right, perhaps in some world this might work. But if you notice that he is giving you a more difficult problem. He's telling you automatic handwriting detection. Firstly, it's not from 0 through 9. You will have uppercase, lowercase characters. You will have other parts of speech. You will have things like comma and such separators. Plus, you will not be given a very nicely segmented 28 by 28 image. Right? So this is the first problem you will have to deal with if you have to do handwriting recognition. Firstly, separate them out into 28 by 28 or something similar kind of boxes. Right? Okay, what else could you use this for? Car number plates, right? If some of you have been to parking lots, and let's say if you've been to any of the nearby malls, if you take a vehicle, the human being does not go frantic and type your car number. It's done automatically via car number plate detection. Similarly, if you go for your pollution certificate, these things are done. Any other place you might use this? Okay, I think we've covered a lot of scenarios. By the way, this is one of the lecture you might want to come early, because the first seat gets the privilege to exercise the neck quite a lot, given the height difference, including me. So there is some advantage of coming in early. Okay, so now we look at the difference between traditional programming and the machine learning way to solve this problem. So your challenge is, given images like this, you have to tell whether, I'm just simplifying it, whether it's a 4 or a not, whether it's 4 or some other digit. Now, how might you think about recognizing a 4? What comes to your mind if you look at a 4? Does it have certain vertical lines, horizontal lines in a certain fashion? Right. So that's perhaps something you might do. If you're not exposed to machine learning, you'll look at 4 and you'll think that mostly all of the 4s are like this. They'll have some combination of a vertical line, a horizontal line, another vertical line, another vertical line going down. But we'll also have to make certain assumptions that the heights of all of these vertical lines, for example, are fairly similar within some tolerance, and they can be also slightly slanted. Right? Not all people write 4 in a particular way, and there are some people who write 4 like the way it's written here on the screen, right? With a 45-degree line. There can also be cases when the 4 is written with a different width. Someone writes with a less width, someone writes with a more width. So now think about programming. Now don't think about machine learning. How might you write a program to recognize 4 using some rules like we've written? Okay, so those of you who've done some basic electronics, you might know what a 7-segment display is. You're trying to write numbers from 0 to 9 in a 7-segment. You have 7 lights which can light up or not light up. So that's one way to think about this. But given 28 by 28 figure, maybe you'll have to use something more sophisticated. So firstly, we need to look at how traditional programming typically works. You're given some data. In our case, the data is the digit 4 and similar digits. You come up with the rules. These are the rules. And typically, you would think of something like if else, nested if else, and apply those rules. Then the traditional program will give you the output as whether this is return true or false. Let's see this in action. I'll show this notebook where I've loaded this data set which is known as the MNIST data set. I'll not go into all of the details. I specifically made these lines to show you that it's a 28 cross 28 image, 28 rows, 28 columns. And each of the value in that cell is a number between 0 and 1. Typically, now I've rescaled it to make it slightly easier for me. Now what I'll say is that I'll first want to show you different kinds of 4s which exist in the data set. Once you've looked at them, you'll perhaps come up with a better way to understand what a 4 is. But in more or less in each of them, you see the same pattern being repeated, right? So I'll be now using what you typically would call divide and conquer, or I'll have certain rules for certain parts of the image. So maybe I'll take this image as the template image, which I want to get correctly. I will break it down, my image, into 4 rectangles. I have chosen these rectangles based on my observations. In the first rectangle, I'm trying to notice whether the vertical edge exists or not. In the green one, again, I'm trying to look at the vertical edge. In the blue one, the horizontal edge, horizontal line, and in the yellow one, the vertical line, right? Now, given this background, how might you write a program? I've given you the coordinates for the red, yellow, green, and blue box. How might you use these coordinates to tell whether the number is a 4 or not? Don't think too sophisticated. The whole notebook, so you can actually see that the notebook is not big. So the code has to be pretty small. I'll take a very, very rudimentary approach. I'll say that if the number of pixels which light up in this region are above a certain threshold, then it exists, then it just tells that there is a presence of an edge or not. Now there are a lot of counterexamples to this, but for the sake of simplicity, we'll ignore them. Right? All we're saying is that look at these rectangles and check the proportion of white is to black in them. If they are within a certain tolerance, within a certain band, then you would say that that condition is met. If all the 4 conditions are met, you say that this is a 4. Right? But as you might be imagining, this is going to work only for a small set of images. Like for example, the 4 that we have chosen, its base vertical line seems to be very small. Whereas if you look at certain other 4s, so this one in fact doesn't even have, so if we were to put this image in our boxes, we may have this line cutting across, right? So this rule will likely fail for this image. So we've just seen that in traditional programming, we give the data, we provide the rules, which is the programmer provides the rules. In our case, we have given certain ifs and elses. We create a bounding box. We look at the number of pixels which are above a certain intensity. We write that program and then we get the answers. That program is something like this. We are trying to, I've shown the 4 different rectangles and I'll just look at the ratios of white is to black. I'll write some if elses, if something greater than something, if else something greater than something, and then I'll run it on different images. On this first image, it predicts it to be not 4. On the second image, not 4. Another image, not 4. Another image, not 4. Right? Is our system a good system based on this? No. Let's look at this line. Our accuracy is 89%. Now, looking at this number, is our system a good system or a bad system? If you get 89% in your course exam at IIT Gandhinagar, would you be happy? So it's a good number. We've just seen that traditional programming, data input, rules input, which you write as the programmer, and you get the answers, whether this is a true or a false, or whether this is a 4 or not. In machine learning, you flip the answers and the rules. You give the data. So importantly, the data is now the image, as well as now you give the answers, which is what specific label that image is. The algorithms will learn the rules which help detect a particular digit. Right? So if we try and understand this through the code, if you notice that when I was trying to detect whether a digit is a 4 or a not, the input that I'm giving is just the digit itself and a bunch of rules that I've created. Whereas I'll now show you the machine learning solution. Before that, so coming back to the the number that I'd shown you, we had got 88% accuracy, but the percentage of 4s which were actually classified as 4s, we'll come up with this term in the end of the lecture. It's known as true positive. That's only 4%. Right? So if you look at all the metrics contextualized to the data, to the problem at hand, you'll understand why this is not a very good system. But if you were to use a machine learning based solution, the only thing I want you to notice is that I am giving in the data or the input, which is x, typically denoted as x, as well as the answers or the labels, typically denoted as y, to the algorithm, which will then internally learn the rules. At the time of when I want to predict for a new image, I will just give a new image as input and I will learn the answer. I will be able to predict the answer, right? So importantly, you should always look at this diagram. For machine learning, you notice that the inputs are both the data, in this case x, and the answers, in this case y, and what you learn are the certain kinds of rules. The specifics of which we don't care about at this point. But here, if you notice, we get an accuracy of 99.47%, as well as the percentage of 4s which are actually classified as 4s as 97.1. Right? So this is a much better, much robust system. We now look at a first ML task after the digit recognition, which is to predict grocery store tomato quality. Now, you have seen a bunch of these online food services like Zomato and Grofers, etc., Swiggy, Grofers, etc. Now, they will be getting bunch of tomatoes, millions of tomatoes every day, which they need to sell. Right? They can't really have a human being look at each and every tomato to ascertain the quality. Again, they'll have to have some automated solutions, some solutions with scale. So, the machine learning problem which I want to pose to you is, can you predict the quality or condition of a tomato given its visual features? So, given an image, given its photo, can you tell me whether a tomato is good or bad? How might you do that? Okay, the color of a tomato will tell you something about its quality. As an example, tomatoes which are very green or very yellow or have a tinge of black are typically not good, whereas a good tomato is typically some shade of red. What other visual features might you use? Shape or texture. So if some tomato is very smooth or very rough, it's probably not a very good tomato. You need something in between. Shape, if tomatoes are square, we never have such, but there can be some very small tomatoes which are typically not good, and huge tomatoes which are not good. Anyone who's done tomato farming, by the way? Okay, I did that in the COVID times in our apartment itself in IIT Gandhinagar. But that's when you realize that actually how tomatoes, some of them good, bad, you can't really control for them quality easily. Some of them you can look for certain patches, certain damages. You could also have certain, like let's say disease in tomatoes, certain white spots which appear. So we have looked at size, color, texture as few important characteristics. Now, if you have to look at machine learning based solutions, we always have to have certain past data collected, which we will use to learn the rules as we mentioned, and then those rules or those machine learning system which we will use for predicting for a future tomato that we see. Right? So we may have a past data set looking something like the following, where we have different samples as well as the different attributes which I mentioned as the features about the particular tomato, color, size, texture, and I have labeled the condition as a separate column, and I've just put a different separator between them. Right? Now, based on the previous few slides, which of them is the data, which of them is the answers? The condition is the answers, it's what you're trying to predict. Right? The other features or the attributes are the data, right, or the inputs. We call them by different names. But should the sample number be a part of the feature input or not? What do you think? How many think it is useful? Yes. How might it be useful? Can you speak a little louder? how old it is? Yes. If the sample number, if the samples are actually not independent, if the sample has some temporal dependence, that can give you a sense of how old the samples are. Or let's say that there is some truck strike going on in some part of India. All the samples which come in from that particular truck will be likely faulty because they would have been delayed by, let's say, 1 day, 2 day, 3 day. So in such cases, sample number can be useful, but typically for this course, we will ignore things like sample number. So let's keep the data simple. We have 3 features: color, size, texture, and one thing which we're trying to predict, which is the condition. I've colored them differently. I'll be calling this entire set as my training set. So training set is the set which I give to my machine learning model as an input to learn the different rules or learn the learn the relationship between input and the output. We see that it contains 2 parts. The first shown in the shade of pink, which is features or attributes or covariates. These are different terms you'll hear for the different terms you'll hear for the same thing used in different textbooks. And the output or the response variable is what you're trying to predict, shown in brown. And we'll typically call this matrix as D. We have very specifically chosen this convention because this adheres very nicely to a lot of machine learning libraries, where you keep the feature matrix as a matrix containing n rows corresponding to n samples and p features corresponding to the p columns. Right? In certain courses, you might see the transpose of this being used, but this is perhaps what is most commonly used in sklearn, like scikit-learn like frameworks, which makes it easier for you. N samples corresponding to n rows, p features, p columns. So each of the sample is p dimensional. So each of the feature we can also write x equal to xi transpose, where I runs from 1 to n. What this means is that we have the first feature, we have the first sample, which is orange, small, smooth. I've specifically written this as a column vector. So typically you always write individual samples as column vectors. You take the transpose of it and you put it in the matrix. That therefore x is n cross p, where each of the row is p dimensional. The output vector is n dimensional. Right? So something as simple as this is usually a good assert to put, that the prediction, the output is matching the size. When we look into things like NumPy, Torch, etc., one of the mistakes which people will end up making is size mismatch, which is sometimes you will have n comma 1 sizes and sometimes you will have n comma sizes. So we'll get to it when we reach to that point. The dataset is typically a tuple containing xi transpose and yi pairs. Now the prediction task, once you have learned your model on such data, is when you're given a new tomato. Let's say for 1st to 3rd January, my system learned the relationship between the visual features of a tomato and the quality of a tomato. Now from today onwards, I want to be taking those tomatoes and predicting the quality. Right? So when I want to predict the quality, I will give the same input features and my system will tell that what is the condition. It will predict this. Do you think what I did is a good exercise? I use my training data set from, let's say, instead of 1st to 3rd January. Okay, so let's use from 1st to 3rd January, and I want to predict from that point onwards, which is, let's say, 4th January till 31st December. Do you think that's a good way to think about this, or are we missing something? What might go wrong? Sorry? The weather will change, because of which, what will change? What constitutes a good tomato will change, right? So similarly, if you've been to the grocery shops inside the campus or vegetable shops inside the campus, you know that in certain seasons, different breeds of different crops come, right? So typically in this time, even if you look at the potatoes, they are less sweeter, right? Has anyone seen that? Okay, none of you are cooking. So the time dependence is also important while considering this. Although at this point of time, we're not considering time, just to keep things simple. So we'll therefore have 2 kinds of sets: training set, which has x comma y, test set, which has only got x, you're trying to predict y. And our prediction task then becomes that you're trying to learn this function, which is mapping from the input features color, size, texture to the output, which is the condition of the tomato. You're trying to learn that relationship. From the training data set, you're trying to learn this. And your eventual aim is to predict the condition for the testing set, which is to replace these question marks with your prediction. Okay. So typically in machine learning, you might have heard of these terms, or you'll hear these terms very commonly being thrown about, either terms like generalization or terms like train, test, accuracy, etc. So let me ask this question. Is predicting on the test set enough to say that, and if the model does well on the test set, can you say that your model is generalizing very well? Any guesses on this? So to answer this, you'll also firstly need to ensure that all of us are on the same page as to the definition of generalization, right? And how are these different samples created? How is the training set created? How is the test set created? How do you think they are created? Are these created by someone giving you a Kaggle data set? Or is there some more process behind it? Yeah. Okay. Okay, so you are talking about randomization, you're talking about, effectively you're talking about shuffling, but that also you have been given a data set. I'm asking how would the data set have been generated in the first place? So for the tomatoes, what do you think might have happened? To create a data set, what needs to happen? Firstly, you need to contextualize certain things. So we'll talk about only Indian companies like Zomato or Swiggy, etc., which means that the population of tomatoes they are dealing with is generally Indian breeds, right? So we are not going to be able to we can't say very confidently that a model will work across the tomatoes that you get across the world. Secondly, you will also notice that the kinds of problems which occur in India are probably different from what might occur outside, right? And then you'll have to also look at where the warehouses are located, where the farmers are, where they get their sites, where they get the tomatoes. All of these you need to consider. So globally, you may see that there is some hidden truth, right, which generates certain data. So there is some genetic information stored in the seeds of the tomatoes. Now the tomatoes are spread across the world. You'll only get a sample of such tomatoes, of the plausible tomatoes that could have been created, right? You'll get some sample collected from some farmers across some parts of India. Right? That is what will constitute your sampling, and from that you'll get your training data set. Similarly, from a different sample, but which has been created using the same process, you'll be able to create what is your test set or where you want to predict, right? So do you see the process? There is some hidden process which you don't know all the details about. If you knew all the physics about how the amount of sunlight it has got, the chromosomes in that specific tomato, if you knew all of that, the amount of water that has been given, the amount of shade in that region, you probably can just use physics and simulate and get the perfect answer. But we will never know that. It's not going to work out. So therefore, we typically just always get a sample from all the possible varieties or possible variations of tomatoes which have been created. One of that sample of, let's say, 1,000,000 tomatoes which we get, we call that as to be the training set. And the other, all the samples that we can create, we'll try to predict on them. Right? But this entire process is important for us to understand what we mean by generalization. Ideally, we want to be able to predict on all possible inputs, which could have been generated using this generative process, but we'll never know them. So typically, we therefore look at a limited sample settings. Whatever samples we are given, we then use the train test, and we're trying to ensure the predictive performance is good enough on test set. We'll look at this in more detail about the difference between a sample and a population, right? Ideally, we should be looking at the population, but we'll always get a sample. That's effectively also what happens when elections happen, right? So you have these exit polls. Are they on samples or are they on the entire population? They're on samples, right? And based on that, they're trying to make certain estimates. Similarly, from given some certain set of samples, you're trying to learn certain generalizations. Okay, so the first task which we looked was specific type of task. We're trying to predict the quality of a tomato. The second one we're going to look at is the prediction of the energy campus of the energy consumption of a campus. Does anyone have an idea of the amount of energy consumption or the amount of electricity bill which we have to pay for running this auditorium for an hour or hour and a half? Can any of you figure that out? Ask around. It's not a trivial amount. We'll have to, this and Jasubai and 300 auditorium, the other one, it's a huge amount. So perhaps when you know that, you'll also be very careful in like ensuring that the sizing is done very appropriately, so that if only for large classrooms you're allocating such things. There are a lot of ACs in this. The bill is typically a big number. Coming back, we want to predict the energy consumption of the entire campus. What do you think it depends on? The season. Typically, you will have more energy consumption in the summers compared to the winters, at least here. What else? Number of people, right? What else? Okay, good. So whether it's a holiday or whether it's a class that day, holidays will typically have lesser, like they'll not have the classes going on that day. So the consumption for these AC halls will be lesser. What else? Which type of? Which type of courses? I think we'll skip the very specifics of that. What are the other kinds of equipments which run inside the campus? So the ACs, if you know, these are typically actually known as HVAC. So these are run based on, some of you might have seen the chillers, right, where you see the water splashing. Right? So the chillers produce cold air which is circulated throughout the campus. HVAC system is one of the larger consumers of electricity. What could be something else? We're studying the machine learning course. If you have to do machine learning, what do you typically need to do? Where do you run your machine learning programs? Not a very hard question. On your laptops, on your computers, on servers. The servers consume energy. So a lot of IT equipment also consumes a lot of energy. Again, if you go to block 5 where the server rooms are, has anyone been inside the server rooms? Okay, so those who've been inside the server rooms, what kind of equipment do you see there? You see the servers which are kept in certain racks. What else do you see? With the GPUs, do you see a lot of cooling there? Because you need to keep the systems cool, right? So that's again a major source of energy. We have factors such as the number of people. More people generally means more energy, not always. Typically, higher temperature generally means more energy required to cool the campus, at least in our kind of country. So if we keep something simple, if we assume something simple as only these two features, we may again create a data set like this, consisting of two parts, the training data set and the test data set. Let's say the training data set contains the number of people we had. So during inter-IT, this number increased a lot, the temperature that we have, the energy consumption that we have, and then we're trying to make this prediction. Right? So related but different question. How do you think the solar energy varies with the temperature? The solar produced. So a lot of the campus gets, we get the sun very regularly in the city. Right? What is the relationship between solar energy produced in the campus and the temperature? It's not a machine learning problem. This is a physics problem. Directly proportional. So all of you think that the hotter the day, the more the solar produce? Okay, let me say this is incorrect. Now, what could be the answer? So in a campus, you may have more produce during February and March compared to June or May. So there is a parabolic efficiency curve or inverse parabolic efficiency curve. So beyond a certain temperature, you lose certain power. There are certain power efficiency factors. So that as an aside. Now we come back to this question. Now you're trying to model the relationship between energy as a function of people and temperature and certain other things. So we've looked at two different kinds of machine learning problems. The first is called classification, which was where we were trying to predict the digit, or we were trying to predict the quality of a tomato, good, bad, something like that. So in such cases, the output variable is a discrete quantity. Discrete means it can take one of k values, one of c values. What other example of classification can you let me know? Can you tell me? We've looked at two examples. What else might you be excited in classifying? Go beyond the course. You're looking at a prediction engine. Who will win the match today? Right. Will the cricket match last 2 days or 5 days? Will my loan get accepted or not? Will I get an admit into IIM Ahmedabad or not? Right. What other things can you predict, which are of discrete outputs? Sorry? Stock prediction is depending on what kind of problem you're posing in. You could pose the stock prediction problem as, will this stock go up or down? Right? In that case, it's a classification problem because you're giving it discrete quantities, discrete output types, up or down. Sorry? Medical condition, do you have COVID or not? Or are you fit enough to play in inter-IIT or not? What disease do you have? Right? What grade you'll get in this course? That's a different kind of a problem because that's not just binary, that's A through hopefully not beyond C. Other classification problems?
Accident detection, depending on traffic.
Accident detection? Okay. So we've seen a few examples. This is where I want all of you to get excited. Think about the different applications you could run into, you might want to run. Regression, we saw the second example, predict the energy consumption of the campus. That's a regression-like problem, where the output variable is a continuous type. Right? Can you give some examples of regression quantities? One was predicting the energy consumption of the campus. What else? Sorry? Sales. Predicting the sales of your product in the next few months. What else? So we're talking about the grades. Can you think of the grades problem as a regression problem? How many marks will you get? Right. Stock problem, we discussed stock problems. Stock prediction. Can you predict the price of the stock in the next trading day? It becomes a regression problem because the output is now a continuous variable. Other things you might want to do? Predicting? Predicting rainfall. So with rainfall like examples, you also have certain other interesting properties. Can someone tell me what is the domain of rainfall?
Yield of crops.
No, it will be generally non-negative, right? So that's another something you'll have to typically consider. For example, for the marks problem also, you'll typically get something from 0 to 100, which is bounded. For range, you'll get something bounded on one side, 0 to positive infinity, right? In certain cases, the energy also you're considering, it will be a non-negative quantity. So knowing such domain, knowing the domains of the output variables is usually helpful. So once we decide that the particular kinds of problems that we want to solve, before we go into the specifics of the algorithms, we want to first know what are our key performance indicators. Have you heard of this term, KPIs, USPs? Right? These are very marketing-like terms typically used. So which will tell you whether or not it's a system is working well. Because until unless you know whether the system is working well or not, you could just keep on optimizing the effort. So metrics help us quantify how well or bad our system is working, our prediction system is working. We'll first look at metrics for classification. So we want to tell whether the classification is working good or bad. We'll be using these symbols throughout the course. The ground truth is typically represented as y, a vector y. The prediction is typically represented as y hat. It's a hat on top of y. Whenever you typically see the symbol hat, it means it's an estimate, it's your prediction. So the ground truth comes from the data set which you have collected, and the prediction comes in from your model, right? So in this case, would you call this a good classifier or a bad classifier? So just to answer that question, we'll need the specific different metrics. We'll first look at the simplest metric, which all of you know, which is accuracy. We'll look at accuracy is simply defined as the fraction of instances which are correctly classified, which means that the prediction and the ground truth are matching. Or you can write it as the cardinality of the set where y equal to y hat divided by the cardinality of the set y, or the number of instances where y equal to y hat divided by the number of instances in y. So in this case, we see that there are 3 examples where ground truth and the prediction match, shown with tick marks. Therefore, the accuracy of this system is 0.6 or 60%. But we often end up using imbalance classes, right? We saw one example of this also, 4 or not. Is the digit 4 or not? I had about 90% of the samples which were not 4 images, only 10% of the samples which were 4 images. This also happens in other kinds of problems. Any thoughts on what other kinds of problems you see this imbalance? Cancer or not? You'll have a lot more non-cancerous patients than cancer patients. When you're trying to detect certain exoplanets, you're trying to detect certain planets. You have a vast universe, you have a small number of that space, small proportion of the space occupied by certain planets. We look at the second metric. I had specifically chosen the imbalanced one earlier to motivate the new metrics that we'll come up with. The next metric is called precision. So here you firstly look at the instances where the prediction is good, right? Or we typically also call it the class 1 and class 0. Bad is class 0 and good we'll call as class 1. That's a convention that we have decided beforehand. So in this case, we look at the examples where we predicted good, 4 examples where we predicted good. Out of that, how many were actually good in ground truth? So 2 of them. So therefore, the precision is 2 over 4 or 0.5. Now, one good way to remember this, the definition of precision is, when you predict when you predict a sample to be class 1 or good, how precise you are in that. Right? So you have to start off with the definition. When I predict it to be a class 1 sample, how precise I am. Right? Of all the instances I predicted to be good, how many were actually good? Right? How precise are you when you predict something to be class 1? The next is recall. It's a slightly different metric. Can someone tell me what you understand by recall? So it is also helpful to think of the literal English meaning of recall and precision. How precise are you when you detect something, and how many of the instances can you actually recall? Right? So in recall, you'll have to look at the instances in the ground truth which were true or the positive class or good. Right? How many of them is your system able to recall? Right? So in this case, we notice that there are 3 ground truth good examples, of which we are able to detect 2 of them in our system. So therefore, our recall is 2 over 3 or 0.67 or 67%. Any questions on these 2 metrics? So yes. So if we have more categories, typically we end up using something known as a confusion matrix, which I'll just show in a second. Just 1 second. So let's imagine that we had a data like this, where we have 100 examples of cancerous or not cancerous we're trying to predict, and we see that the prediction has 1 yes, 99 no's, and the ground truth has 99 no's followed by a yes, and just forget about the that's a typo. Right. What is the accuracy of the system? 90? 98%. So you should be very happy. You have obtained 98%. Would you be happy? No. What is the precision? So precision means you look at all the instances where you predicted yes or positive or true. How many such examples do we have? 1. Out of that one example, how many examples are actually yes? 0. So the precision is 0 over 1, which is 0. What is the recall? You look at all the examples where the ground truth is yes. So how many true cancer patients is a machine learning system able to recall? 0. So the accuracy of 98% has no meaning over here. You have precision and recall both to be 0. This is also evident if you make something known as a confusion matrix. You have a 2 by 2 matrix where you look at the rows as predicted to be yes or no and the columns to be ground truth yes and no, and you put this large 98 number here, no being detected as no, but you know that a very dummy classifier would have also got the same numbers, right? So we also have 4 different points in this matrix, in this 2 cross 2 matrix, and they're also given different names. The ground truth is yes and the predicted is also yes. It's known as true positive. We are truly detecting so we have detected the positive correctly. The ground truth was no, but we predicted yes. We falsely predicted a positive. The ground truth is yes, but we predicted a no. So we falsely predicted as negative, and the ground truth is no, but we've also predicted it to be no. So we've truly predicted the negative class. That's the way you need to remember this. This confusion matrix. You don't need to remember, you need to look at any definitions, just literally go to ground truth is yes, I have also predicted to be yes, I have truly detected the positive. Ground truth no, I have predicted yes, I have falsely detected it to be positive, and so on. Okay, based on this, can you now tell me the definition of precision and recall based on true positive, false negative, true negative? First, the definition of recall. So for recall, firstly, what did I say? You have to look at the ground truth instances which were positive. So ground truth instances being positive is the first column, right? Now out of them, how many have you been able to predict positive? That is TP, true positive, divided by the total number of instances in which the ground truth is positive. So TP divided by TP plus Fn. So if you look at this confusion matrix, you will be able to get the metric quite easily. You don't need to remember anything. Of the fraction of instances in the ground truth which are positive or true, which of them is a system able to detect correctly? Okay, similarly, what is precision? Again, the way to think about this question is, you have to think of which row or which column you want to color. So for precision, we said that we want to look at the quantities or the samples which we have predicted positive or yes. So which means we have to look at a certain row or a certain column? The first row. If you look at the first row, how many of them have we actually predicted correctly? Which is TP. So TP divided by TP plus FP becomes your precision, right? So this is a good exercise. If you just do this once or twice, you'll be able to remember this for the rest of your life. You don't need to remember you don't need to come up with certain ways to remember this formula. I think just draw the 2 by 2 matrix. You'll be able to get this. There is a metric which is combined based on these 2 metrics, precision and recall, which is known as the F score, which is 2 times precision into recall divided by precision plus recall. If you remember your AM, GM, HM, what kind of mean is this? Harmonic mean of precision and recall. There is another metric known as the Matthews correlation coefficient. This becomes specifically useful when we have a lot of imbalance in the data. So complicated formula, but given a data like this, can you now quickly tell me the precision? You need to calculate, you just need to tell me the numerator and denominator. 90 over 94, the recall is 90 over 91. The F score is something you'll calculate. All of these numbers seem to be pretty good, right? If you notice, the precision is good, the recall is good, the F score is good, but the Matthews coefficient is poor. What does this tell you? Matthews coefficient is a metric specifically designed to help you understand class imbalance and the performance under class imbalance. And here you see that you're not doing a very good job, right? Even a very simple classifier which predicted always positive would have given you good numbers, right? So there was a question on the confusion matrix and if we have multiple classes. So we have currently looked at two classes, positive, negative, but we've said classification we can do for any number of classes. So this is what we may get if we do confusion matrix on the digit recognition problem from a multi-layer perceptron on a neural network which I have trained. So firstly, do you see that the true label and the predicted labels seem to be transposed from what I had been drawing? Right? So this is something you'll have to be very careful when they give you the confusion matrix. You have to look at the rows and the columns. Sometimes people make the transpose of this. Right? So then always don't just choose the first row or the first column. That definition may change depending on the axis that you have. So if we have this confusion matrix, what can you say? Is this a good system or a bad system, machine learning system? What do you think? Okay, is this useful in any way? Why might I use this complicated matrix instead of just reporting the accuracy? Assuming no class imbalance. If there is class imbalance, of course, you might want to use F score or something similar. But in the absence of that, what do you think? Might be some utility of drawing the confusion matrix.
It predicts 5 as an 8 many times.
Sorry?
It predicts 5 as 8 many times.
Okay, good. The name of the matrix is what matrix? Confusion matrix. You're looking at the confusion between different classes that you're predicting. Right? Can you look at this diagram and tell me which two digits get confused the most? 5 and 3. So you look at this. So along the diagonals, you're predicting the number correctly. Right? So there is no confusion. You're trying to look for large numbers which are in the off diagonals. We look at a number 15, which is the true label is 5 and predicted as 3. Do you sense that there can be some confusion between 3 and 5? They visually look similar. We have another one which between 2 and 8. Again, there is some similarity in the circular way in which 2s and 8s are done. Some more confusion between 4 and 9. Again, if you write 4 in a specific way, it might look like a 9. So this is very helpful to understand qualitatively as well as quantitatively understand where you may have certain confusions, where you may need to improve your model on. We can also look at the specific notebook which I used to create. And once we have this, I wanted to show the specific examples where the confusion was happening. The true label was a 5, but it's predicting to be a 3. Do you think this could be a 3? Possibly. So these are examples where the human being may also get them wrong, right? So therefore, a lot of people sometimes recommend what is the human baseline to figure that out. So a lot of you may end up using something known as the ImageNet data. If you have not heard of it, you will hear it in some point of time. There's also a human baseline in that. If you gave those images to a human being, how accurate they are. And sometimes it's incredibly hard. Like this also very similar to a 9. This may be predicted to be 7 or 9. These are very hard examples. Right? So this is to give you a sense of what your system is, what you're trying to predict. Now when we come to the metrics for regression, we don't really have a metric known as accuracy. Why not? We are on a continuous scale. So we can't really say that if the ground truth, if the energy consumption of the campus today was 200 megawatts and you're predicted to be 200.000001 megawatts, it's a mismatch. You're not accurate because it's not exactly matching. That's not what you do for real quantities. You look at the errors. So if these are the two predictions and the ground truth, again predictions shown with a hat, y hat, and the ground truth shown with y, we look at this specific quantity, mean squared error. You might have heard of this metric a number of times. One simple way I suggest to remember this is to look at the colors and the order. First, you find out the error. So mean squared error, first find out the error. The error is yi hat minus yi for the ith example, right? First find out the error, then square the error. So find out yi hat minus yi, then square the error shown in green, and then take the mean of it. The mean of it is yi hat minus yi square from I equal to 1 to n divided by n, right? That's a simple way to remember this. The other commonly used metric is the root mean squared error, which is the square root of MSE. Now, why might you prefer root mean squared error over mean squared error? Imagine you are measuring the energy consumption of the campus in megawatt hours. What are the units of mean squared error? Square of megawatt hours. What are the units of root mean square error? In the same range, right? So you'll get a sense of in the same space, in the same units you'll get. What other metric could you use for regression? I've shown a square here. Could you have avoided the square?
Absolute.
You could have used an absolute value also. So everything else is the same, but the square is changed to an absolute error. But my question to you is, why not use the mean error instead? Why have the bothering of the square and the absolute just to make things more fancy?